We will discuss low-level file access. Each running program is called a process which has a number of file descriptors associated with it. These are small integers that we can use it to access the open files or devices. But how many number of file descriptors are available, or how many of these file descriptors are available, will vary depending on how the system has been configured. When a program starts, it usually has three of these descriptors already opened. These are 0 represents standard input, 1 represents standard output, 2 represents error, that is a standard error file descriptor. We can associate other file descriptors with files and devices by using the open system call. The file descriptors that are automatically opened, however, already allow you to create some simple programs using write system call. The write system call arranges for the first n bytes from the buffer to be written to the file associated with the file descriptor, and this write system call returns the number of bytes actually written into the file. Sometimes this may be less than n bytes if there has been an error in the file descriptor, or if the underlying device driver is sensitive to the block size. If the function returns 0, it means no data was written into the file, and if this returns -1, there has been an error in the write system call, and the error will be specified in the global variable, the name errno. There is a global variable name where the error will be stored. So now we'll see the syntax of the write system call. The syntax of write system call contains three parameters, that is a file descriptor which is of integer type. Another one is buffer, where we want to store or where we want to write the data into the file is available in this buffer, and n bytes. So this n bytes I specified already, as the file descriptor returns the number of bytes actually written. So this may be less than the n bytes if there has been an error in the file descriptor. So this n byte represents how many number of bytes that the file descriptor, that the write system call is going to return. So that is the syntax of write system call. This is an example program where I have implemented the write system call. In the if condition, I am specifying the write system call with file descriptor 1. The file descriptor 1 represents the standard output file descriptor. And I want to write the data. Here is some data /n. So this is the data that I want to write it onto the standard output file. Means I want to write the data onto the monitor, because the standard output file is represented as a monitor as an example, comma, the n bytes value specified here is 18. The write system call is going to return the number of bytes that is written now. If the number of bytes written here with the help of write system call is 18, and 18 is not equals to 18, the condition is not satisfied. Otherwise, if it returns less than 18 or greater than 18, the condition is satisfied. When the condition is satisfied, it will try to execute the write system call where the file descriptor 2 is specified, which is called standard error output file, onto which the data that is represented in double quotes, that is a write error has occurred on file descriptor 1, will be written into the standard error output file, and it will return the number of bytes written into the file. Here the n bytes value is 46. That is the number of bytes that it wants to write into the file. So when I execute this program, the output that we may see here is some data, because the number of bytes available in the string is 18, including the new line character. So the if condition is failed and it will not execute the write system call with file descriptor 2. It will execute the exit system call with 0, where 0 represents true. That means it is going to close particular program. So the output here is some data. Now we'll discuss about read system call, which reads up to n bytes of data from the file associated with the file descriptor, and it places them into the data area called as a BUF, that is a buffer, and it returns the number of data bytes actually read, which may be less than the number requested. And if a read call returns 0, it had nothing to read, so it reached the end of the file, and again an error on the call will cause it to return -1. So the syntax of read system call is shown on the screen, which contains the three parameters like the same in case of write system call, but in case of write system call we're using const, that is a keyword which represents constant. That means the string that I want to write into the file should be constant in case of write system call, but while I'm reading it is not specified as constant. The first parameter is same compared to write system call, that is a file descriptor of integer type, and the third parameter is same compared to write system call, which is n bytes of type size underscore t. In write system call or in read system call, the size underscore t represents it is a type of integer. Now we'll see a simple example program, so which copies the first 128 bytes of standard input into the standard output. That means the main intention of the program that I'm going to show here is to copy the data from one file to another file, where the intention is to copy the first 128 bytes of standard input to the standard output. That means it copies all the input if there are fewer than 128 bytes. This is an example program of read system call, that is a buffer array with 128 bytes. Nread is an integer variable used to hold the read system call returned value. The read system call is going to return some value if it is success by reading the data from the standard input file of size 128 bytes. If nread equals to -1, then it is going to return a read error has occurred, that is a string to be written onto the standard error file. If nread is equals to -1 is failed, that means if nread is not equals to -1, then the next if condition, that is a write system call of 1 comma buffer comma nread, that will be executed, and when the write system call is success, it is going to return some value, and if that value is not equals to nread, then only it will enter into the if condition and it will execute the write system call by specifying a write error has occurred onto the standard error file. Otherwise it will not write the error message, it will simply write the buffered content onto the file. Now I will discuss about the open file descriptor. So to create a new file descriptor, we need to use this open system call. The syntax of the open system call is containing the following header files, like file control header file, that is fcntl, then system/types.h, then system/stat.h. These are the three different types of header files that are required for open system call. One representation of the open system call is with two parameters. One is the path name of the particular file, another one is o-flags. The another notation of the open system call is with three parameters along with these two, that is a path and o-flag bits. It also contains mode bit. So this is about the syntax of the open system call. In simple terms, open system call establishes an access path to a file or a device. If successful, it returns a file descriptor that can be used in read, write, and other system calls. The file descriptor is unique and it is not shared by any other processes which may be running. If two programs have a file open at the same time, they maintain distinct file descriptors. If they both write to the file, they will continue to write where they left off. And the data is not interleaved, but one will override the other. And each keeps its own idea of how far into the file, that is the offset, it has read or written. That means how many number of bytes that it was read or how many number of bytes it was written so far will be available with the particular file descriptor. the name of the file or device that is to be opened is passed as parameter, that is in the first parameter, that is path. The O flags specifies the parameter that is to be used to specify what are the actions to be taken on opening the file. Normally, the O flags are specified as a combination of mandatory file access mode and other optional modes. The open system call must specify one of the file access modes shown in the following table. One is O underscore RDONLY, that is open for read only. Similarly, I have one more mode called open for write only. Then another mode for open for read and write. So these are the three different modes which are mandatory file access modes that we need to specify. The call may also include a combination using a bitwise or of the following optional modes in the O flags parameter, that may be O underscore append, where I can place the written data at the end of the file, and O underscore truncate to set the length of the file to 0, discarding existing contents, and O underscore create creates the file if necessary if the permissions given in the mode, and O underscore excl, it is used with O underscore create to ensure that the caller creates the file, and the open is atomic, that is it's performed with just one function call. So this protects against two programs creating the file at the same time. If the file already exists, then open will fail with the help of this O underscore excl. If the file already exists, the open system call will fail, otherwise it will create a file. And this open system call returns the new file descriptor. Always it may be a non-negative integer if it is success, otherwise it returns -1 if it is failed. And it can also set the global variable error to indicate the reason of the failure if it is an error. And the new file descriptor is always used by other file descriptors, which is the lowest numbered unused descriptor, a feature that can be quite useful in some circumstances. For example, if a program closes its standard output and then calls open again, the file descriptor 1 will be reused and the standard output will have been effectively redirected to the different file or a device. Here the global variable where I am going to write the error into the file, I already specified it is a err info. I am going to show the name of the variable, that is err info, shown in the bold letters on the screen. The number of files that any one running program may have open at once is limited. The limit usually defined by the constant open underscore max, which is available in limits.h, which may varies from system to system, but POSIX requires that it be at least 16. But on Linux, the limit may be changed at runtime, so open underscore max is not a constant, which is typically starts out at 256. Now we'll see another topic, that is initial permissions. When you create a file using O underscore create flag with open system call, the mode bit, that is a third parameter in the second syntax, which is made from a bitwise R of the flags defined in the header file system/stat.h. So these may be the following, that is s underscore irusr, that means read permission for the owner. Then s underscore iwsr specifies write permission for the owner. Similarly, s underscore ixusr means execute permission for the owner. In the same way, s underscore irgrp represents read permission for the group, followed by write permissions for the group and execute permissions for the group. And in the same way, we have read permission for others, write permission for others, and execute permission for others. So now I will show you a simple example where I am showing the open system call. In this open system call, I am specifying the file my file. If the file is available, then it is not necessary to create with the help of O underscore create. If the file is not available, then O underscore create will create the file by specifying read permission for user and execute permission for others. So when I execute the ls command, I will get the output like this, where the owner is assigned with read permissions and the others is represented with execute permission. There are a couple of factors that may affect the file permissions. First, the permissions specified are used only if the file is being created. Second, the user mask specified by the shell's umask command affects the created file's permissions. The mode value given in the open call is 100 with the inverse of the user mask value at runtime. For example, if the user mask is set to 001 and the s underscore ixoth mode flag bit is specified, the file won't be created with other execute permission because the umask specifies that other execute permission is not to be provided, and the flags in the open and create system calls are in fact requests to set permissions. Whether or not the requested permissions are set depends on the runtime value of the umask. So now see the umask, where umask is a system variable that encodes a mask for the file permissions to be used when a file is created, and we can change the variable by executing the umask command to supply a new value, and the value is a 3-digit octal value. Each digit is a result of ORing values from 1, 2 or 4. The meanings are shown in the following table, where the separate digits refers to user, group and other permissions. The first digit represents the user, that is if the digit value is 0, no user permissions are to be disallowed. If the value is 4, user read permission is disallowed. If the value is 2, then user write permission is disallowed. If the value is 1, then user execute permission is disallowed if it is the first digit. In the second digit, if the value is 0, no permissions are disallowed for group. If it is 4, read permission is disallowed for group. If it is 2, write permission is disallowed for group. If it is 1, execute permission is disallowed for group. Similarly, in the third digit, if the value is 0 means no permissions are to be disallowed for others. If it is 4, read permission is disallowed. If it is 2, write permission is disallowed. And if it is 1, execute permission is disallowed for others. For example, to block the write and execute permission for the group and to block the write permission for others, the umask would be represented like this. The first digit is represented with value 0, where no permissions are disallowed for the user, and I want to block write and execute permission for the group. In the second digit, it relates to group, so I want to block the write permission and execute permission. The value for write is 2 and execute is 1. So I need to specify those two as a value for the second digit. That means by bitwise ORing, we will get 3 here. And the third digit, it is represented with 2 because I want to block write permission. So the umask value will be 0, 3, 2. The next system call that we are going to discuss here is close system call. We can use the close system call to terminate the association between a file descriptor and its files. The file descriptor becomes available for reuse. It returns 0 if it is successful and -1 on error. So now I'll show you the syntax of the file descriptor, where I'm going to specify only one parameter that is represented as a file descriptor of integer type, which is returned by the open system call. Note that it can be important to check the return result from the close. Some file systems, particularly networked file systems, may not report an error while writing the data into a file until the file is closed, because data may not have been confirmed as written when writes are performed. I'll see the last system call, that is ioctl system call, which is a bit of a ragbag of things. It provides an interface for controlling the behavior of the devices and their descriptors and configuring the underlying services. Terminals, file descriptors, sockets, and even tape drives may have ioctl system calls defined for them. The syntax of the ioctl system call contains the following parameters. One is the file descriptor, another one is the command, and we have some optional parameters also. So we will see the parameters now. ioctl performs the function indicated by the command, that is a cmd, and the object referenced by the file descriptor, that is the first parameter, which may take an optional third argument depending on the functions supported by the particular device. For example, the following call to ioctl on Linux turns the keyboard LEDs on. That is ioctl within the parameters list. I am specifying the first parameter is the file descriptor of the keyboard. The second parameter is the command, is I want to set the keyboard LED lights on or off. Then the optional argument, that is the third bit. The third optional arguments are LED underscore num. That means I want to set the num lock LED. I want to set the caps lock LED, and I want to set the scroll lock LED.